In example 3, we're going to look at an exponential function in context. So we're going to start with a population of a city of 4.6 million in the year 2010. It's growing at a rate of 1.3% for each of the next 4 years. So then what's the exponential function that could model that growth? So in year 0, start with 4.6 million people. All right, that was given. After 1 full year, if it's growing at 1.3%, we're going to multiply the 4.6 million by the 0.13. All right, that's the amount that we're going to add to the 4.6 that we started with. So in essence, you can write it as 4.6 times 1.013, where the 1 represents what you started with, and the 0.013 represents the growth in 1 year. In the second year, you would multiply it by another 1.013, right? Because you need another year's worth of growth. If you're multiplying it by two 1.013s, you can really just write it as 4.6 times 1.013 squared, where the 2 represents the 2 years worth of growth. So for year 3, you could just make the exponent 3. For year 4, you could just make the exponent 4. So if we look at the model for a generic year, P represents the population after, again, any year you want, any amount of years that you want after 2010. The population that we started with in 2010 is the 4.6 million. The growth factor is the 1 plus the yearly rate, so 1.013. And then the exponent t represents the amount of years since 2010. We can then use that function to get the population at any given year after 2010, again, assuming that the growth rate is 1.3%. So what we're going to do is use that fact to figure out what's the growth or how many people are in the city in 2040. So in 2040, it's been 30 years since 2010. So we're going to substitute 30 in for the exponent, evaluate that expression, and you get approximately 6.78, meaning in 2040, the population will be about 6.78 million. Why don't you try these two you try it questions? So pause your video. Take special note that the B value here is less than 1. So consider whether you think the value of this printer is going to increase or decrease, given that the B value is now less than 1. So you can try these questions, pause it, try these questions, then come back and we can compare answers. All right, now let's compare answers. For part A, if it wants the value of the printer after 10 years, we're simply taking that 10 and substituting it in for the exponent in the function that was given to us. So that's what we're seeing here. When we evaluate that function, 30 times 0.93 raised to the power of 10, we get approximately, so round it, 14.52. So assuming the printer was $30, probably is more than $30, but whatever. So let's say if you start it with the original value is $30, it's now worth $14.52 after 10 years. Does the printer lose more of its value in the first 10 years or in the second 10 years after it's purchased? Definitely the first 10 years. It's already lost more than half its value. So it can't lose more than that in the second 10 years, just logically. But also if you consider, right, coordinate plane, a decay function is doing this, right? So let's say that's 30 there, right? It's steeper in this section of the graph than it is in this section of the graph, meaning it's losing more value there than it's losing there, right? It's losing less value each year as it goes on. That's why the curve is starting to level out as you move to the right. So that's just generally how it would be. So same thing with a growth function, although it's reversed, right? As it's going up, it's starting to get steeper, right? So if you think of a growth function, so if this was asking about the population in the city, right? Starts here or whatever and goes up, right? It's steeper up here than it is down here, meaning it's growing more as the years go on. Okay, so let's take a look at example 4.